Today's topic is errors, estimation of errors, and how to test if x equals to y. Okay, what are errors? When we do numerical computing, errors are not mistakes. Mistakes can be avoided if we make effort, but we can never just remove errors. When we do numerical computing, errors are like a shadow, the shadow of some object. Say like we walk under the sun, we always have some shadow. You cannot remove the shadow. Errors are due to, three sources. One is due to observation. You just ask yourself, can you get the exact length of, say, one side of your table? We cannot. So the value we measure, say the length, the side, the length of one side of our table, it's just an approximation. We cannot get the exact value. How precise our ruler is, it doesn't matter. Okay, we always have some error due to observation in that case. And when we do numerical computing on computers, we will have two more types of errors. One is called runoff error. That's due to the constraints of computer hardware. Say, for example, you can see pi. We know pi, this is pi. We know pi is an irrational number. So when you do some calculation involving pi, you need to choose a value, and the computer cannot, cannot save infinite many decimal places, right? Okay, so you need to pick up a value. When we pick up a value, say usually we use 3.14, and we say that's the value of pi. Actually, that's the approximation we choose. It's because we choose so, we'll delete all other decimal places, all the remaining, well, how many? For pi, in that case, it's infinitely many terms which will be truncated. That's truncation error. It's due to our choice. We choose 3.14 as the value of pi. So in that sense, we do this. We choose to do so. We human beings, we programmers, we choose so. That's that kind of error here. As said, the truncated part is the truncation error. And even you choose 3.14 as the value of pi in the operations, complicated operations, maybe in many tables, and computer will still could have runoff error, like pi take squared or so, and the sine of some value, cosine of some value, and when you evaluate the computers, yes, due to the hardware constraints, computer has runoff error. This, in some sense, is somehow you may believe it's beyond our control. Okay, if we work on a computer, yes. Later we'll see we still have a little control. So when we do numerical computing, we have two types of two types of error we need to consider: runoff errors, truncation errors. As per the errors due to observation, that's not the issue of just numerical computing. Okay. It's always there. You do computing on computers and calculators or not. It's they are there. Okay. And total error, we have a concept. It's called total error. That's the effect of all which one the runoff error, truncation errors in our computing. Yes, we put them together. That's the total error. And truncation error also in this class, especially in from chapter 8 on, it's about numerical differentiation. Okay, we have formulas. Say, to find the first derivative of a function at a point, you have multiple choices of formulas. If each formula may have involve, yes, each one will involve truncation error. You choose one with, you can, of course, you may say, I choose a formula with a better accuracy. Sometimes you don't have the choice. Okay, sometimes we do have the choice. We also need to, even we have the choice, we still need to consider something else like runoff error and which thing and the computing time. Okay, now truncation error in many cases in this course is due to, as I said, the formulas we choose is due to, hey, this Taylor series expansion of a function. I don't know if you like infinite series sequences or not. They're very topical. That's taught in calculus 2. Okay, with the Taylor series of a function, yes, with a function, it's Taylor series expansion at now normally we just consider here at the x is 0. Okay, you see the exponential function e of x, its Taylor series expansion at 0 is this. It involves infinitely many terms, and theoretically, of course, if you have infinitely many terms, the two sets are equal to each other. They are exact. Okay, values. And when we do computing, we cannot say if we want, given that a programming language you use doesn't provide how to evaluate the exponential function, and you may use this Taylor series expansion to approximate it. And now your choices is that, our question is that, could you use infinitely many terms here? No, we can never. That's impossible job. We only use a finite number of terms. One term, that's not good. Two terms, made a little bit better. And three terms, four terms, five terms. And we know theoretically, mathematically, algebraically, analytically. Anyway, we have so many words here. Okay. And the more terms we choose, the better approximation will be obtained, right? That's something we know. But how about numerically? That's something, a big difference between, yes, the pure math and the numerical computing. Okay. Numerically, this is not always true. Okay. Why? The more terms, first of all, the more terms involve needs more computing time. You may say, oh, that's fine, I don't mind that much. Okay, the issue is runoff error. The more terms are using, each term could have runoff error here, and the accumulated runoff error could be large. That's why not here when we do numerical computing. We should know. Okay, Okay. Machine epsilon. If we follow the IEEE 754 standard and we express a number in double precision, if two numbers in floating point numbers, okay, in double precision, if they are of the same order, the smallest difference between any two such numbers are given by this. Okay, such a number is called machine epsilon. And MATLAB, LUO plus Mathly also each provide such a constant. You can directly use it in your code. Yes, machine epsilon EPS. Okay, now problems. How to test if two numbers are equal to each other? If two numbers are integer numbers, no problem. You can use this way to express it. You can test, hey, x equals 2y, that's fine. Remember is two equal signs. Okay. If x and y, two numbers, are integer numbers, you can simply use this. You can use that one to test if they are not equal. How about in floating point? For two floating point numbers, or simply speaking, two real numbers. Okay. Can we just use this to test if they are equal to each other? No. We cannot do this. After this lecture, you may try to experiment with on your calculators or so. You do this. How about 2? You take a square root once, square root twice, square root 3 times or more times. Okay. You get a value. Say, how about just this? You take a square root of this and I square it. Square it. Okay. Will this be 2? You see if we can get that. Okay. I doubt. If your calculators tells you, hey, this is equal to this, okay, they give you exactly 2. You say you do this operation, it gives you 2. In many cases, you should believe your calculators are cheating. Okay. Okay. So they try to let people believe they could do a good job. Okay, normally they should not be exactly the same. Now here, when we code, we cannot, for two floating point numbers, we cannot say use this to test if they are equal to each other. Now, how to do it? You say, okay, is the value, the absolute value of the two numbers less than epsilon? Yes. If yes, now that means you say, hey, that means they are the same, no difference. Okay, we use this. It depends. Sometimes you can check the source code of my LUO plus my Mathly module. Sometimes as you times epsilon to make it a little big, because so many times you don't need that precisionness, right? So, okay. So you may use, say, 10 times this, 100 times this, no big deal. Okay, so it depends. Normally, so many times when you see, we should know that for floating point numbers, if we want to test if they're equal to each other, we use this to do it. That's why here in the code we use this. Is that tests if this value, the function's value at mid, is 0 or not. If it's greater than epsilon, that means it's not 0. Okay, that's the second one. The second one is, oh, if it's greater than this, or greater than 10 times this. This depends on your choice. Okay, on the very question, problem. And normally people will do this, so you'll see, commonly you'll see things like that, code. And you read, possibly, you'll see so many times in your textbook, the source code just uses things like this. That's really bad. Okay, that's a mistake. There are mistakes. Okay, they should not do this way. And I wish you will pay attention to things like this. Textbooks, many textbooks, I believe, the authors possibly they don't code. They ask their graduates, also graduate students, to code. Okay, to write the code. So just pay attention. This is a very important thing we need to know. Okay, tolerance. Tolerance, as you can see, what's that? Literally, is it's how much you can tolerate. It's the maximum error, maximum deviation you can tolerate. Okay, that's called tolerance. Okay, to error. Given that, that's how to estimate errors. Okay, given that you have exact solution x, we denote that exact solution like x sub t is true solution. And now we can get yes, if the value we can get is x, numerically is ns, x sub ns, the true error is the distance between, I said, what's error? Now we'll see what's error. Error is not mistake. Error, simply speaking, error is the distance between the value we can get, obtain, and the exact value. Okay. Normally that's the definition of error. Okay, so you take absolute value of the difference. Okay. Is that a good measurement? Not mentioning. Okay, of course here. If we already know the true exact solution, what's the point? In many cases, we need to find an approximation, right? If we already have the exact one, we don't need to find the approximation of that value normally. So the case is, we want to find an approximation to some values because we don't know that value. That's the case in most. That's most of the cases. Okay, we don't know this guy. Therefore, if you don't know this guy, how can you find the true error? Therefore, you cannot. And now the problem is, oh, I can find the numerical approximation and s, and I even can get an even better one, an s prime. And I can, in next step of iteration, I can get an even better one. Okay. Therefore, the true error, in many cases, you cannot do this. You say, oh, therefore, I can get two approximations. And how about the error? That's just estimated error. You say, oh, there are difference. Okay. Now the question is here, that kind of error, true error, estimate error, do them make sense? In many cases, they may not make sense. Why? And you just choose this. How about this? It said the mass of the carbon-12 atom is this small, that amount of grams. Okay. Therefore, how about if this is exact solution, XTS, Given that you can find a numerical one, you try your best. Is hey, is this, you get this value. Now you test. Is hey, is this minus this less than, say 0, 0. I believe this is a very small number in many cases. I say, hey, put one more 0 there. I said, that's very small. Does this test make sense? If this is true, you mean this is a good approximation? Or this is not true. Okay, now you get this. You say, how about I get this? 4. If you have this value and this value and this value, put it into this test. If you believe this is a very small number, now you calculate the difference. You take absolute value. Yes, this is true. Therefore, you believe that's a good approximation of the mass of the carbon 12 atom. Of course, that's very, very poor one, right? So therefore, normally we don't use such kind of a measurement of error. It's not a good measurement. Okay, so normally we use relative error. Relative error. We don't use such kind of error or true error or so. The estimated error, we use relative error. Okay, the true relative error is this. How about it's this way? You get it. Given that we know the true solution x sub ts, you get a numerical subsolution x sub ns. The quotient here, this one I take as absolute value, and that's a way better measurement. So in most cases, you will see people use this, the relative error. Okay, we measure the relative error. Again, the problem is, in the true relative error, we don't know the true solution in most cases, so therefore this doesn't work. And that's why in so many cases we use estimated relative error. In the iterative algorithm for at each stable we'll get an approximation of some value. So like at the ith stable you get x sub I, and the next stable is the previous stable xi minus 1 sub the next one x sub I plus 1. Okay, now we use this to, and we use this to measure relative error. Okay, it's called the estimated relative error. Here you see this. I use this. x0 is this one, x sub I minus 1. x1 here in the code is x sub I. Okay, so you see that's in the code. We use estimated relative error, and that's a topic on algorithm. The two they are taught. We started the two algorithms in chapter 3, solving nonlinear equations. Okay, that's yeah. So we just finished the estimation of errors. We're talking about errors now. Your book something that doesn't mention. Your book uses this big O notation. The big O notation, but it something like it doesn't address this. The authors possibly assume in many books they assume readers should have the knowledge. So in case you haven't started big O notation, or you started before, I just give you a brief introduction or review. Okay, big O notation. We say there are two cases. Okay, we say f of x is big O of g of x. If not we can always say f of x is big O of g of x. For any given two functions, there must be conditions to be made. Okay, For f of x and g of x, if there are two, of course, positive constants k and m, they are called witness of such a relation. Okay, f is bigger of g. Okay, for such a relation, we say k and g are witnesses. Okay, if there are positive constants k and m, so that okay, this relation is true. The absolute value of f of x is always less than or equal to m times the absolute value of g of x whenever x is greater than or equal to k. And this, and it sounds like some textbooks, they just give us a definition in this case. That's simply for when x goes to infinite. Why? And this is in computer science, this is a commonly used notation, big O notation. Okay, it's this. You have a given that x is the problem size, and when the problems say, what's the problem size? Say, for example, if you want to find a number in a group of numbers, you want to find a number x in a group of numbers here. That group of numbers, how many are there? Given that they have m numbers, and that m will be the problem size. Okay, and when n is small, you can always find such a value. You can find if it's there or not. Okay, in the list quickly. If it's a small size, our problem is theoretically when n is large, or in other words, when n goes to infinite. Could your algorithm, your code still can find the number in the list quickly? Or in anyway, that's the problem. We normally will always consider the case when the problem size goes to infinity. Okay, and actually we in our class, we don't care this case. Normally we don't. We care the other case. When x goes to 0, it's getting smaller and smaller, the quantity. Okay, and actually in our case we use h, not x. It's h increment in x, also h. Okay, that's when h goes to h. Normally it's a stable size. Okay, in chapters 8, 9, 10, 11, we'll use this. Okay, and this time we do what? We say, hey, this guy is less than, whenever x is less than or equal to such a k. And because we are talking about inequalities, so in some books they drop equality in that case. That's fine, no big difference. Because if we have this relation, is true, you choose this when larger, that will be less than, right? Yes, so it doesn't matter. They are the same. Actually, they are equivalent. Okay, so don't mind. Now, say for example, we have such a function. And for the fourth case, now we're talking about the fourth case. You see, how about that? You just try to examine this. Okay, this, and you take absolute value of the, say, 4x cubic, 3x squared, 5x plus 11 by the triangle inequality. We know this is less than or equal to 4x cubic plus 3x squared plus 5 absolute value x plus 11. And now, how about this too? When x, hey, you say, hey, when x is greater than or equal to 11, we try to get rid of the constant. Say, hey, this is plus 5x, because x is greater than or equal to, we under this condition. Okay, Now this will be x, right? So we combine like terms, and so we will have, therefore we will have this stable. I move this, okay, and this is less than, that's just equal to 4x cubic plus 3x squared plus 6x. That's under the condition x is greater than or equal to 11. Okay, we have this. Now, because we know under this condition, because x is greater than, that's less than or equal to, okay. And now, x is greater than this, so therefore, this is less than or equal to 4x cubed plus 3x squared plus x squared, right? Because this is 6 is less than 11. So therefore this is equal to 4x cubic plus 4x squared. That's, so under the condition we have this 4x cubic plus 4x squared. Again, it's under the same condition, x being greater than or equal to 11, so this is less than or equal to 4x cubic plus x cubic, because 4 is less than, which one? This 4 is less than 11, right? So you have this, so you have 5x cubic. So therefore we have f of x is big O of x cubic. We have this is true. Oh, we have witness for such a relation. We have which one witness? What's k? K is 11 here, 11, and m is that 5. M is 5. Okay. So we have this. Therefore, eventually under this, we have this is less than or equal to 5x cubic. Okay, so we have this. And please notice that this one, the big O notation is not unique. Why? Because here x is less than, it's greater than or equal to 11. So therefore this, as you can tell, this guy is less than 5 is less than 11, so that's less than x times s cubic, right? That's x to the 4. Come on. It's this. In that case, you can also say f of x is big O of x to the 4th. And this guy is less than x to the 5th, right? Because x is greater than or equal to 11. So you can also say f of x is big O of x to the 5th. And so on. Originally we get this. And so on. Okay. So it's not unique, but in that case, when x goes to infinity, in that case, we always choose this one as our answer. This one with the smallest number there, power there. Okay, so, okay, that's this. That's the first case. How about the second case? Now we talk about the second case. X goes to 0. For the second case, with the same function, we see, oh, this is, again, by triangle inequality, it's 4x cubed plus 3x squared plus 5x plus 11. And let's see, what will we get? X goes to 0. How about we'll say x goes to 0. What will we get? X goes to 0. Okay. So if x is in the range from -1 to 1, exclusive. Okay. And now this will be less than which one? As you can see, 4. And this 3, less than 3. This will be less than 5, right? Plus 11. That's how much? That's as you can tell, 9, 20, 23. So it's a big O of 23? No. 1. We'll write 1 there. Okay, that's 1. Because 23 is 23 times 1. We use that. We'll not use a 23, 100 there. Okay, it's constant. Okay. That's this case when x goes to 0. Okay. With big O notations, there is something we need also to know that say if you have therefore for the second case, if f of x is such a, if you have such a relation, we say, hey, this it's g of x plus, okay. What should we do? We say in the second case, if you have this is big O, if we use h to measure the distance between the two, okay, h is a function of h. If it's this or h squared also, for example, okay, and we can also write this f of x plus, from the first one, algebraically we'll do this. If we move big O notation, that term to the left hand side is this, right? But here, that's ugly. We still put, it shows the relation between f of x and g of x. That's to measure the, you may say, hey, how about the truncation error or the error? Okay, so that's the difference. We don't mind. It's positive and negative here. And another thing is this. It's not pure. It's not correct algebraically. Okay. If you follow that, if you understand it, it's fine. Okay. The other case here, you don't mind. Say, how about 3 this? You can drop this 3. Not 3, 300. 100 is still can drop the constant. Okay, so it doesn't matter the constant. We don't like the constant. We just use 1. Okay, because what? That m. Okay, so that's this. So big O notation is used everywhere. Yes, in quite a few chapters. Okay, that's this. Now, finally, this is not directly related to our topic today. Okay, so but I still need to mention, with our residential program, we offer a course, Math 133. It's called Math Lab or so. Okay, anyway, it's a 1 credit hour class, and it's required for math majors, minors, I believe so. Okay, and then we did a survey with each graduating class before. Okay, we did this. And it turns out some or many complained. They they complain this course is useless because they have never used mathematics since they have passed the class. Oh, was the very problem. And fourth, the survey itself is a problem. It just asks the students to evaluate which courses courses are more important, which courses they use more, they love more, or so. And some just complain they had not used it again after since they finished the class. The survey question is a problem. It's like this. You just ask, if we put a question like, hey, there is say Euler's method, do you believe it's useful? Some students will also complain if we put such a question there. Oh, since I finished studying that method, I had never got a chance to use it. Therefore, it's useless. That's not a fair question. Okay, the question survey is always a problem. The second problem, it could be this. Some students, they, after years taking the class, they just forget about this. They don't want to use it again. That's your choice. Mathematics is a very good tool. Later I discuss more. When we do math, it's one good tool. Another tool is MATLAB. Now you have another choice. LUO plus math. Okay, so after you have started one language, programming language, also you need to practice to use whenever you get a chance to use. This is like with human language. I have started quite a few human languages: Russian, Japanese, German, Esperanto. Oh, English. I speak my native language is Chinese. Now, yes, I had to spend over 3 years on German. I could read and write. I could communicate with professors in West Germany 30 years ago. Now, I knew nothing about the very language. Basically, nothing. I just like a good morning, good evening. Oh, so I can say this. Okay, what's the problem? We need to practice. Whenever we have the chance, we need to try. If you love some tool, don't just quit using it. Whenever you have a chance, use it. Don't say, oh, I have a physical calculator, I just use it. It's convenient. Oh, convenience, of course, it matters. But if your computer is on, why not just start MATLAB or Mathly? LUO plus Mathly, why not? Okay, there are super calculators. Okay, and so that's a problem. Some possibly they just they don't mind. Okay. Now I need to we just spend a few more minutes about this. You have MATLAB or LUO plus Mathly. Why mathematical? We should know that there are different products. MATLAB or LUO plus Mathly, they are for numerical computing. That's numerical computing. You evaluate an expression or function or so. You do some operations and you get a number throughout the whole process. Your code just manipulates numbers, values, numbers. Or so you eventually get a number as the final answer. Okay, that's numerical computing. That's a simple way to describe it. Okay, how about symbolic computing? Now, could you use MATLAB to do this? It's hard to say. Actually, it's yes. If you install extra packages for symbolic computing. Okay, how about LUO plus Mathly? Sorry, I didn't add the feature. That's painful. A lot of energy, effort will be made. Okay, I quit. I don't want to make it big. I want Mathly, LUO plus Mathly to be tiny, to be my daily computing tool. Okay, and a convenient tool, fast tool. So, simply speaking, MATLAB cannot do this, and LUO plus Mathly cannot do this. Okay, why? The software will manipulate the symbols. Sine is a symbol, x is a symbol, cosine symbol, x symbol, cosine sine are functions. That's the strength of mathematics. Mathematics is good at this, at symbolic computing. Okay, so we have two types of tools for computing: numerical computing and mathematical computing. You know the tools. Therefore, when you have some job to get it done, to do, you know which tool to use. The different tool, the very tool will help you get the things done just comfortably, easily. If you choose the wrong tools, it could get things done, maybe, but it's painful, ugly, you don't feel comfortable. Yes, we want to work happily, joyfully, right? With pleasure. I don't want to do things very painfully. I hate. If I have to do things I hate, oh, that's really painful. That's that's not the things we like. Okay, so knowing tools and in which case for what kind of job should you use which kind of tools. That's our talent, our ability. Yes, that's extra things. Just like I told engineering students, if you with calculus 3 or some classes, I encourage them to use mathematics. I just tell them because I assume they all were good at MATLAB. Okay, I say, if you put a resume like your resume for a job, okay, like this, it's, hey, I'm good at MATLAB. No, it gives you, this statement gives you no credit because you are supposed to be good at MATLAB. If you say in another way, say, hey, I'm good at mathematics and MATLAB as well. Oh my goodness. The viewer of your resume will believe you are somebody. You know the right tools for the right jobs. Okay, so anyway, thank you.